All right, today we are going to review for tomorrow's Unit 9 test. So if you would please follow along, we're going to run through all of the lessons just like we always do real quick, point out the important definitions, formulas, things like that, and we'll go from there. Okay, so the first thing we talked about, and this was way back before spring break, is we talked about the brand new term solids. Now, solid was a new term to us, okay, and basically what we discovered was that the word solid was just kind of a catch-all term that dealt with the family of three-dimensional shapes. And we said solids could have a whole bunch of different properties, so it was difficult for us to make just blanket statements that applied to all solids. However, we did determine that there are little subcategories that different parts and pieces of solids fit into, and that kind of generated a new vocabulary for us, and it's that vocabulary that's that language that we've been speaking here in Unit 9. So let's have a look at some of the terms that we've been talking about. We said that all three-dimensional solids are built out of two-dimensional polygons, and we called all of those polygons faces. However, the term faces is not used all that much. The only time we actually have the term faces is if a question asks us how many faces does a solid have. Okay, but more frequently, more often what we have to do is we break down those faces into two different subcategories, and it's those subcategories that help us out with a lot of the calculations and the classifications that go along with our solids. Those two classifications were, number one, bases. Okay, and we talked more about bases as we went forward, but at this particular point, all we said is there could be no bases on a figure, there could be one base on a figure, or there could be two bases on the figure, and it really depended on some other stuff that's going on in the solid. And then secondly, we said we have the lateral faces. Everything that is not a base in a solid is then a lateral face by default. And if you add up all the total number of bases and lateral faces in a solid, that gives you your overall total number of faces. Then we said everywhere that those faces join together, a line segment is formed. And that line segment is called an edge. Then those line segments join together, and everywhere those line segments join together, they form vertices. Now, we came across a formula, and you may need to refresh your memory on this one. It's been a while since we talked about it. It's called Euler's formula, and Euler's formula accurately relates the number of vertices, the number of edges, and the number of faces together by this formula. And the formula says vertices minus edges plus faces equals 2. Now be careful when you are using this formula. Okay, the F for faces, that's not just the lateral faces, that is the total number of faces, including the bases. So very simple formula, plugging in, solve for your missing value, and it'll tell you exactly what you need to know. We ran into the term the vertex again. The vertex happens in a three-dimensional solid if it only has one base. If a figure only has one base, that is fine. Across from that base, you will find the figure comes to a pointed location, and that's what we call the vertex. And remember, that's a strange naming situation. Do not confuse the vertex with a question that says how many vertices does a figure have. Okay, the vertex is a vertex, but it is the only vertex that can be called the vertex. If a figure did not have just one base and the vertex, then that typically meant that it has two bases. And these figures are pretty easy to spot because somewhere in the figure you will have two parallel congruent sides that we can call bases. Now, something like a rectangular prism over on the left side, there's a lot of opportunities to find locations where we can say, hey, here are two opposite congruent sides, so I can call those bases. We could call the top and the bottom bases, or if we chose, we could call the left and the right bases, or if we chose, we could call the front and the back bases. But remember, the maximum number of bases you can have in a figure at a time is 2. So wherever you put the bases in a rectangular prism, all the rest of the sides are going to be lateral faces. In the pyramid, or the cylinder over on the right side, there's only 2 locations where we have parallel opposite sides that are congruent, so those must be the bases of the figure. We haven't really worked with the sphere very much. We'll get into him a little bit more next unit. Okay, but it is possible that we have spherical or spheroid type objects that do not have any locations that are parallel or congruent, or really anywhere that we can call a base and a vertex. Okay, so in this case, we have figures that do not have a base, and the entire skin of this figure would then be a lateral face. Okay. We also came across a couple of measurements on this first day. The first one being height, and of course keep in mind that when it comes down to geometry, height does not often have anything to do with just being straight up and down. The height in a solid measures the distance from a base across to the vertex, or from a base across to the other base. And those measurements happen when the measurement is perpendicular to the base that you're measuring away from. Okay, we also came across the slant height. Slant height is from the vertex. It only happens in pyramids and cones, and it's from the vertex down the lateral face until it connects with the base, and it connects in such a way that it's perpendicular, and that's slant height. As we worked forward with some of our calculations, we saw that we were able to build triangles inside of our solids using the regular height and the slant height and the apothem, and we went from there on some of our formulas. Okay, that was the end of it. So basic vocabulary, and it's important to get a good grasp of that vocabulary because that is the language that the tests are going to speak to you in. For the next several days, we spent time talking about surface area and volume. Okay, we started off with surface area of prisms. Now, surface area of prisms is a little bit of a trick. There's not really a true clear-cut formula that we work with. Okay, before we got to that, we put a basic definition on surface area. Surface area is simply the amount of stuff required to cover a solid. So surface area is all the stuff around the outside. Okay, and we took that stuff that's around the outside in order to calculate the surface area, and we unfolded it all and we laid it down flat, and that's what we call a net. A net is what you get when you unfold a solid and look at all of its pieces lying flat. And I offered you some basic strategy on finding the surface area of prisms. Okay, first, if the figure was not drawn transparent, as this top figure is not, then I suggested that you go ahead and draw it transparently by putting in the hidden edges, okay, drawing them in, dotting them in, so that we can see the figures that are actually there. Okay, and then take your figure and discover what the net is going to have in it. And we do that by kind of allowing the figure to fall apart at its edges that are sticking up, allowing the lateral faces and the bases that are not on the bottom, allow them to fall apart. And like in the case of this rectangular prism that has a roof on it, we'll want to swing the roof out of the way so that we can see all 6 of the sides of the rectangular prism laying down adjacent to each other, and it might help you to label the particular sides like I have on this figure right here. Next thing you said you needed to do was to take the measurements from the original figure and transfer them to your net. And be very careful with this step. It's easy to put the measurements in incorrect places. And if you do that, it's likely going to cause you some calculation issues. Okay. After that, you can kind of identify which faces you have are going to be congruent to which other faces, and that can save you a little bit of time as far as your calculations are concerned. Okay, from here on out, it's simple 6th grade math. You've got area of rectangles, possibly area of squares, possibly area of triangles, and those formulas are all found on your formula chart. So you just calculate them up, add them up, and then you end up with a surface area. Okay, same thing over and over again. If it's not transparent, draw it transparently, allow it to fall apart, get your net, transfer your measurements, figure out which areas you have may be the same to each other, and then calculate your basic areas using your basic formulas, add them all up. The cylinder, remember cylinder's kind of a special case. Okay, surface area of a cylinder is obviously 2 circular bases, but this lateral face that wraps around it is a rectangle, and that rectangle is exactly long enough to reach around your circular bases one time. That's circumference. Okay, so calculating the circumference for that length of that rectangle. And again, you can go back and you can look at your notes and you can watch the original video if you want to see some of that in slower motion. From there, we spent time after that also looking at surface area of pyramids or cones. Okay, now surface area pyramids and cones a little bit more straightforward because there is a formula that goes along with this one. And that formula will say one of two things. Either it'll say 1/2 PS plus big B or 1/2 PL plus big B. Now the P represents the perimeter of the base, big B represents the area of the base. The difference between these two formulas is the little s or the little l. And that's just a vocabulary difference. Okay, little s represents slant height, which is what I tend to call it, and little l represents lateral height, which is what the tax formula chart has called it from time to time. Okay, but just be aware of that. Slant height, lateral height, they both mean the same thing. From here on out, all you have to do is basically apply the information that you need to the formula, 1/2 PS plus big B. Just walk through the variables and go, okay, P, perimeter of the base. Did they give it to us? If not, can I calculate it? S, slant height or lateral height. Did they give it to us? If not, can I maybe build a triangle and calculate it? Big B, chances are they're not going to give you big B. They're going to make you calculate that one. But remember, all we're dealing with on the bases is typically regular polygons, like squares, like regular triangles, maybe a regular pentagon, a regular hexagon, something like that. And those formulas are on your formula chart. Calculate your values, plug into your formulas, and get your answer back out of the formula. It's really pretty straightforward. The only thing they can do to you is change the figure and change the type of information they give to you, like they did on this triangular pyramid. Okay. And of course the cone. Just keep in mind when you're dealing with circular bases, you're going to need circular formulas. Okay, area of your base, it's going to be a circle formula. Perimeter of your base, that's circumference, going to be a circle formula. Okay, so there's that. After that, we switched gears and started spending some time talking about volume. Okay, volume of prisms. A straightforward formula on the formula chart for you. The formula is volume equals big B, little h. Big B being the area of the base, little h being the height of the prism. Okay, and once again, it's just walking through the figures, finding looking at the variables and going, okay, big B, did they give us the area of the base? Probably not. They're going to make us calculate it. And the height of the prism, maybe they give it to us, maybe they don't, but we're going to figure out what it is and we're going to plug in. And this is just kind of rinse, wash, repeat. This is pretty easy stuff. And of course, keep in mind with the cylinder, make sure you use your circular formulas to get those. And the cube, volume of a cube, okay, side cubed. Okay, the length and the width and the height, they're all the same value, which is whatever a side length is, an edge length is, so it is that value to the third power. Next, we went to volume of pyramids and cones. Okay, once again, we have a formula, and what we discovered is that the formula for the volume of pyramids and cones is exactly 1/3 of what the formula was for the volume of prisms. Okay, so 1/3 big B, little h. So this is the exact same stuff over and over again. Okay, figuring out big B, did they give it to us? If not, we're going to calculate it. We're going to plug it in. Little h, the height of the pyramid, did they give it to us? If not, we're going to calculate it, plug it in. But it's just walking through the variables, build triangles when you're missing information. Okay, the same stuff over and over again. Okay, after that, we've gotten a little bit more technical here with our Unit 9 stuff here lately. We finished up with cross-sections of solids and perspectives. Now, cross-sections, this is probably the thing that's giving people the most mental fits, and it's not that it's such a difficult concept, is that it's challenging to our imaginations, trying to figure out when you cross-sect, which means taking a solid and cutting it, what exactly does the cross-section look like? Okay, which is, if you took an apple or something like that and took a knife and cut it and then picked up half of the apple and looked at the inside of the apple, the part that you just cut open, what type of a shape is it? It's the same idea with cross-sections, and we started off by talking about this little cylinder here, and we said, you know what, when you cross-sect this thing, it could you could cross-sect it and end up with a circle if you cut straight across it. However, if you cut through the body at an angle, you ended up with an ellipse. And you said, well, hey, we could also cross-sect this thing by cutting it straight down through the bases, in which case we might end up with something like a rectangle. And we actually went online a little later on and we looked at the cross-secting of a cylinder, and we even found some additional shapes beyond those three that I just provided you with. Okay, so you may want to watch the video on that one again if you're still struggling with it, and of course take a look at these two websites. Okay, these, if you play around with these can really kind of open the doorway in your mind as far as understanding what all can happen by cross-secting different angles through different types of solids. And that was your assignment, was to spend a little bit of time doing this. So if you never did bother to do that, you might want to consider doing it. Okay, the questions that they're going to throw at you, you're not going to be able to do it with a website. You're not going to have these figures sitting in your hands. Okay, you're going to have to do it with your mind. Okay, after that, we spent a couple of days looking at some different information on perspectives. Okay, so perspectives. Now, the perspective idea is simply the idea of looking at a figure from different perspectives, different positionings. Okay, being able to look at a figure on paper, understanding what that looks like in real life, and then further understanding that figure in real life. What would it look like if we looked at it from the left side, or from the right side, or from the top, or the bottom, or the front, or the back? Okay, there's really no telling how they might do it. Now, typically they tend to stick to questions that look at it from front, left, and top, and that's why we did those activities from those three perspectives as well. Okay, but what we did is on the first activity last Thursday, I gave you free rein to build any four figures that you wanted using 8 cubes going in 3 different directions, and then you were supposed to draw the 3-dimensional view of this thing, and then the front view and the top view and the left view. The next day we got a little bit, even a little bit more technical than that, and we learned the official names for these guys. That 3-dimensional view, the one that everybody had so much fun trying to draw, that's what's referred to as an isometric. The prefix iso means same or even. And so we're looking at a 3-dimensional drawing where we can see the left side and the front side and the top side all in the same view. Isometric, prefix iso means same. Orthographic, the term orthographic, that refers to the particular 2-dimensional views of our structure. Okay, so important to know that, just in case they happen to throw some vocabulary at us. Okay, and I believe that's it. That kind of brings us up to speed. Yesterday, all you did was had that worksheet that tied everything in, and that is due today. If it has not been picked up already, okay, the substitute's going to get that here in a moment. At any rate, okay, I'm sorry that I'm not there to answer any questions that you have over worksheets or previous quizzes or things like that in person. If the sub is capable of doing that, I'm sure he or she will be happy to answer any questions that you might have. If you need to visit any other math teachers in the building, they will certainly be happy to assist you while I'm not there as well. And I will be back at school Wednesday morning at my normal time around 7:30. So if you do have questions, definitely come in and ask them. Okay, I'm sorry I'm not there for the review, but the test will go on Wednesday as scheduled, one way or the other. Okay, so be sure to study hard, look on Edmodo, watch any of the videos, or perhaps watch this review over again, and walk into class on Wednesday prepared. You will get a formula chart on Wednesday. The rest of it's going to be up to you. Good luck.